All right, so we didn't exactly finish Chapter 4 last meeting, and so that's what I'm going to do today. If you're looking at your notes, if you're following along with your notes, it's the last page of your notes. It's page 8. And so as you're looking at page 8, there was actually there's several examples on that page. And I believe that I ended up going over these examples here. And so what I have left for today is to do the top examples. And so these were the top examples. Okay. All right, so we were talking about, we were looking at the section on counting. And so the reason counting is very important is because we should be able to know how many possible outcomes there are, because that's your denominator. When you find a probability, the total number of outcomes is what goes in your denominator of the probability that you're looking for. And so we went through various counting rules, and the last two we talked about were permutations and combinations. And so here we are looking at finding the probability of winning a lottery with the following rule. We're going to select 6 winning numbers using the numbers 1 through 44. So if you're looking at numbers 1 through 44, then you have 44 numbers to select from. We're not including 0 here, so it's just 1 through 44. Okay, so 1, 2, 3, 4, 5, 6 numbers, that's what we're allowed to select. So this right here, this represents my ticket. So if I go out and I purchase a lottery ticket, I am going to choose 6 numbers from 1 through 44. Now, there are no repeats, so I can't select the number 1 twice. I can't, if I selected once, that's it. I can't select it again. There are no repeats. And for permutations and combinations, that's one of the requirements. We cannot have repeats. It's all without replacement. So if you look at the definition on your notes, I'm just reading it here, but the definition on the notes for combinations and permutations, it says we select R of the n items. It's done without replacement. So without replacement means that there are no repeats. There are no repeats. Okay? All right, so I am choosing 6 numbers here, and I want to find the probability of winning the lottery with the following rule. The numbers can be chosen in any order, and there are no repeats. So order here is not important. The order in which I select the numbers is not important. As long as I select the winning numbers, I have the winning ticket. But the order in which I select the numbers does not matter in this case. So we had 2 rules. We had permutations and combinations, which was the rule where order did not matter. So we can call it NCR and NPR. So one was combinations and one was permutations. Right, so if you go back to your definitions, you'll see which one tells you that order doesn't matter. And Stephen typed it out for us there. Good. All right, so the NCR, that's where order doesn't matter. If you rearrange, it's the same count. So when you rearrange, you get the same count. Order does not matter. So to count how many possible selections there are from 1 to 44 when you select 6 numbers, you have to use the NCR to help you count that. Okay? All right, so this is how we're going to write it out. From the 44 numbers, you're going to choose the 6 winning numbers. Or it's just the 6 numbers. We don't know if they're going to be the winning numbers, but we're selecting 6 numbers. Okay, so that counts the total number of ways it's going to happen. The total number of ways you can select 6 numbers from 44. So I had showed you the formula for that in your notes, in your Chapter 4 notes. If you look at the NCR, which is your combinations, you'll see the formula. And you know what? I just opened up the calculator and I see the problems that we worked on. And I might have already done this problem. Okay, but I don't remember that I did. Okay, so I'm just going to go over to the So how do I know that I did the problem? Because look at the calculator. It's on there. Okay, so we have 44 and CR 6. But I didn't find the probability, so it's odd. But that's okay. We'll go ahead and review it. As I don't have the probability on the calculator, I would have just, I must have not finished it. Okay, so just to remind you, I'm going to clear that. And so just to remind you, NCR, there's 44, so you have to type in the number first, 44. And then you go to math, because that's where your probability is, right? So PRB, using the right arrow key, gets you to probability, and then the NCR is number 3. So you can just press the number 3, or you can go use the down arrow key until it's on number 3. Press enter, and there's 44 NCR, and I believe we had 6 numbers we were choosing. So that's how many possibilities we had. Now, I didn't answer the question about the probability. I just found the possibilities, the total number of outcomes, the total number of ways we can select 6 numbers from 44. Okay, so I'm going to write that down. All right, so if I write this down, it's 70590529052. Okay, so let me put appropriate commas there. So it's 7,059,052 ways of selecting 6 numbers from 44, from 1 to 44. All right, so the probability then of having the winning ticket, probability of W, the total possible outcomes is the 7,059,052, and there's only going to be one winning combination, okay, and that's the numerator. So there's only going to be one winning combination of numbers, and that's your numerator. Okay, now you could write that as a decimal or scientific notation. It's probably a very small probability. So if you go back, let's go back to the calculator and see what it looks like. So I'm going to do 1 divided by, so it's going to be 1 divided by my answer. I don't want to have to type all that in again. So the way that I get answer is I go second and then the answer key, which is the negative key at the very bottom. And so I just did 1 divided by my previous answer. And there it is. So it's the probability. You have a numerator denominator. So write it in scientific notation or write it as a decimal. So it looks like it's 1.4 2 times 10 to the negative 7. And now writing it as a decimal, just make sure that you are rounding to 3 significant digits. Now that is the rule for probabilities, that we always round to 3 significant digits. However, some of you have already noticed that on the homework, it tells you to round just to 3 places. And the reason for that is probably the fact that if you do get a very small probability like this one, somehow the system isn't set up, the homework program isn't set up to handle that. And so it's just easier for you to just round it to 3 places. But on the midterm, you want to make sure that you're rounding probabilities to 3 significant digits, just like we've been doing in class. on the homework, they changed the rules, so just make sure you read the fine print. They do have instructions for how to round. All right, so if I want to write the probability here, I'm going to put 6 zeros in front of the 1. So there it is. All right, so it's unlikely. That's the reason we would turn it into a decimal to answer questions whether it's an unlikely probability or not an unlikely probability. Well, this is definitely unlikely. And it's unlikely because it's smaller than 0.05. Okay. And there's a good question. We talked about this in my face-to-face class. So do you see how we were able to count all the different number combinations that there are when you're selecting 6 numbers from 1 to 44? So in reality, if you were to find out what all those different combinations were and buy that many tickets, 7,059,052 tickets, yes, you would be ensured that you would win. So back in the 80s, I think a group of people got together and they tried to do this. And so this is already known that it can happen. So you kind of watch out for people who are trying to buy this many tickets. But yes, you can be guaranteed to win if you know how many possibilities there are. I'm sure there are rules. There's something in place for where the state will they'll be able to catch people if they're doing that, if they're pooling. It's interesting. I haven't heard anything lately, but that would be interesting to find out what the rules are for that. But yes, technically, if you buy 7,059,052 tickets representing all the possible combinations, you would be assured to win. Now, my example, it did not include a mega number because now you have a mega number, right? Or they have, they add up, they put something different. So then that would increase the number of combinations. Yeah, but that is an interesting point. Okay, so it would be interesting to see what the exact rules are for that, because there might be some restrictions as to how many lottery tickets you can purchase. All right, for the next one, now it's the same problem except that the rules are changed. So in addition to selecting the correct 6 numbers, you must now select them in the same order as they're drawn. So now it has to be the same order. Okay, so let me just remind you that for the previous one, assuming that the ticket that I purchased, I chose these numbers. That I chose those numbers. That was my ticket. I went and I purchased a lottery ticket, and those are the numbers that I chose from 1 through 44. There are no repeats. And so if I have the winning combination of numbers, for the first example, it doesn't have to be in the same order. So say that the numbers are drawn in this way: 40, 39, 1, 3, 5, 2. So say that the drawing, the numbers were drawn in a different order. Well, according to the rules now, you're still a winner. As long as you have the winning numbers, you're still a winner. So that was the scenario for the first example. It doesn't matter what order I select my numbers. If I have those winning numbers, then I'm a winner. But for the second scenario, that's not the case. Even if you have the winning numbers, you're only a winner if you selected them in the same way that they were drawn. All right, so that probably will bring you to an even smaller probability of winning, because now that you're changing the order, you're creating different counts. When you change the order, you're creating different counts, and that's what we talked about when we looked at permutations. So for this bottom one, this would be a permutation, because order gives, when you change the order, it gives you a different count. In this case, the order matters. Now I just put a C in there. I meant to put a P for permutations. Order matters. So it's 44 and it's for P, and so in this case order matters. All right, so on the calculator I'm just going to go ahead and put that over 44. So it's very similar to the combinations. I have to type in the 44 and then go to Math, select Probability by using the right arrow key, and then NPR. There it is, option number 2. I press Enter and it was choosing 6 numbers out of the 44. So I'm expecting to get an even larger number of outcomes, because when you change the order you get a different count. And so that's what we see there. So look at my denominator. Before the denominator was 7,059,052. Well, now it's much larger than that. Much, much larger. Okay, so the probability, you have a numerator and a denominator. So there's only one winning combination. So there's only one winning arrangement of numbers. So it's going to be 1 divided by that total number that we just got. So second answer just gives you that puts that in the denominator. So your previous answer is now in the denominator. Wow, that's e to the negative 10. So it's really, really small. So 1.97, I round that to 1.97, and that's a much smaller probability. Okay, so now the probability of winning is 1 over that amount. And so that gives me 1.97 times 10 to the negative 10. So there's 9 zeros in front of the 1. All right, so I was saying there's 9 zeros in front of the 1, and I put a 9 there. All right, so 9 zeros. And then I have the 1, the 9, and the 7. All right, so much smaller probability of winning. Unlikely. It's an unlikely probability as well. More unlikely than the previous example. Okay, and so this is how we're going to use the counting rules. It will allow us to solve more complicated probability questions, and it allows us to find the total number of outcomes that we're looking at. It counts the total number of outcomes. So it gives you the denominator portion of your probability. That's what the NCR and the NPR give you. It's the denominator portion of the probability. Now, in some instances, I will ask you a question where I'm asking to find the probability, and that's what I did for these two. But in other instances, I'm not asking you for a probability. I'm just asking you for how many ways something can happen. How many ways can something happen? So there, you don't have to have a numerator denominator. You're just going to find whatever the rule gives you, the NCR, the NPR. You're just going to find the total number of outcomes, but it's not a probability. So you just have to be careful what the question is asking. Okay, so I felt like I didn't spend enough time on this last time, or maybe I just rushed through it, but this is what I wanted to get through, and I do believe we covered, I'm pretty sure we covered this second example, because I know that I asked you questions about this on the lecture problems, on the lecture questions that I have at the end. Okay, all right, so today, let me know if you have any questions. If not, then we're going to go ahead and move on to Chapter 5. So at this point of the semester, you should be looking you should be working on your StatCrunch assignment, which is posted on my Stat Lab. Don't wait until the midterm to work on that, because it's a mistake a lot of students make. And if you're working on it the week of the midterm, you're not going to be studying for the midterm. It's going to be very overwhelming if you wait until the midterm to work on that. So make sure you get started on that StatCrunch assignment as soon as possible. Right? That is going to be submitted to me. You're going to print it out and turn it in on the day of the midterm. So work on it as soon as possible. My instructions, I feel, are clearly written. Any problems that you are going to encounter may be because you have a different version of Microsoft Word, or maybe because you are working on a Mac, or something that's not what I wrote the instructions for, and they're very similar. It's just you kind of have to troubleshoot. You have to make sure you're able to work through it. So technical problems is what you may run into. So please get started as soon as possible. That way you still have time to come and ask me questions if you run into problems. Okay, but don't wait until the week of the midterm. It will be too overwhelming. So get it done as soon as possible. All right, so I talked there hoping that maybe if someone had a question they would type it out, but I don't see any questions. So I am going to continue. Okay, so in chapters 2 and 3 we talked about descriptive statistics. So in descriptive statistics we found the mean, the standard deviation. We found measures of center and measures of spread, which is measures of variation, right? And then we took a break from that and started talking about probabilities in chapter 4. So in this next chapter, we are going to combine the two previous chapters. We're going to take what we know about descriptive statistics and take what we know about probability, and we're going to combine them and talk about probability distributions. Right, so we're just combining the methods from the earlier chapters. Now, a reminder that on my Stat Lab I do post the notes that I'm going over. I do have a condensed version, which is a PDF version, which students seem to prefer just because it's not as overwhelming as the PowerPoint. And so I'm just trying to pull that out just to show you real quick. But just know that both versions are on my Stat Lab under the under lecture notes. All right, I'm just trying to pull that out, and here it is. Okay, so if you have the condensed version, this is how it starts. Okay, and so this is kind of, I try not to put too much on here, and I focus on the key points. So if you're following along using the condensed version of my notes, that's what it looks like. Okay, but of course I also have the PowerPoint on there, and I also save it as a PDF just because I can save 4 slides on one page, and so if you're trying to print it out, you don't have to print too much out. But again, if you print this part out, this has everything you need. All right, so just know what's available under lecture notes. When you go to my Stat Lab, the lecture notes are posted there, and I do it for every class meeting. I put the date on there, and I list them on there. Okay, so again, as I mentioned, this chapter deals with constructing what we call discrete probability distributions. So we're mainly going to focus on discrete probability distributions. The next chapter, we are going to look at continuous probability distributions. But for right now, we are focusing on discrete probability distributions. And as I mentioned already, we're combining the methods from the earlier chapters using descriptive statistics and probability. Now, what probability distributions allow us to do is probability distributions will allow us to describe what will probably happen instead of what actually did happen. So you're describing what will probably happen instead of what actually did happen. So we need to be able to know the probability that is associated to the random variable that makes up your discrete probability distribution. And I'm going to talk more about those vocabulary words, those new words that I just used. Okay, so here's a visual. In probability, we talked about the procedure, right? Rolling a die is a procedure. Tossing a coin is a procedure. So a procedure is conducted here. And in Chapter 4, we talked about the probability of every outcome. So you have a procedure, and then you know what the probability of each outcome is. We are going to organize that information into a table. Now, if you actually collect your data, if you roll a die and you're collecting your data, that's what this table does. You actually collect data. So that's what we did back in chapters 2 and 3, where we collect data, we find the mean, we find the standard deviation. So in descriptive statistics, we collected data and we found the measures of center and the measures of spread. And that's what we have here, measure of center and measure of spread. In chapter 4, we found probabilities without actually conducting an experiment or collecting data. We just found our probabilities. What we're doing now is we're organizing that in chapter 5, and we're creating a theoretical model. And this describes how the experiment is expected to behave. So the one of the columns, the X, that's our random variable. And it's a discrete random variable. And remember, that's from chapter 1, discrete. Okay, so you see how discrete, they're countable numbers. 1, 2, 3, 4, 5, 6, they're countable numbers. So one column represents all the possibilities when you roll a die. Those are discrete. They're countable. And then the next column is the probability that's associated with that random variable. So we're going to organize that information in a table, and then we're going to look at the measures. We're going to measure what's happening by using the mean and the standard deviation. Okay, now, very important, what has changed here? Look at the notation for the mean and the standard deviation. It is different than the notation we used back in chapters 2 and 3. Since probability distributions are describing what will probably happen instead of what actually did happen. So we're making predictions. All right, so then what the notation that we use are Greek symbols for population. So this gives you a visual of what you should expect to see in chapter 5. So we're combining what we've already done, the descriptive statistics with the probability. All right, and that's what I just went over. So this section introduces the important concept of the probability distribution, which gives the probability for each value of a variable that is determined by chance. And that variable, I called it a discrete random variable. So we are going to talk about, and there have been some changes on the new editions. I just want to make sure I'm looking at that correctly. We give consideration to distinguishing between outcomes that are likely to occur by chance and outcomes that are unusual in the sense that they are not likely to occur by chance. So don't get the likely and unlikely from what we talked about in probabilities before. we're going to get to this a little later. We've already talked about unusual. How do we determine if something's unusual? So if something's unusual, it's the mean plus 2 standard deviations or the mean minus 2 standard deviations. Anything above 2 standard deviations or below 2 standard deviations is considered unusual. That's different than unlikely. So for unusual, we had a maximum usual value and a minimum usual value. Anything above 2 standard deviations of the mean is unusual. Anything below 2 standard deviations of the mean is unusual. So that was our definition for unusual. And then we had a definition that we used for probabilities when they were unlikely. So if your probability was unlikely, then it was less than or equal to 0.05. So that's different than unusual. So the question would either be, is this unusual or is this unlikely? And you have 2 different comparisons. Okay, so a random variable on a table, your random variable would be the column for x. That's your random variable. And then the other one would be your probability. So you're going to have a table. It's your probability distribution table. One of the columns is your random variable, which, by the way, is going to be discrete. And discrete means it's countable. And then it's the probability associated with that random variable. Okay, so in this chapter, we're focusing on discrete random variables. So they're countable. It's a finite number of values or countable numbers of values. It refers to the fact that there might be infinitely many values, but they result in a counting process, so it's countable. Now, continuous is different because that comes with a measurement. So continuous random variables, that comes from measurements. And so we're going to focus again on discrete. Chapter 6 is where we're going to see continuous random variables. All right, so here's an example. And this is where I start my notes on the condensed version, the one that I had showed you a few minutes ago. That's where my notes start. Okay, so that's the first example we're looking at. The rest is just an introduction to the chapter. So here's an example of a probability distribution. This probability distribution is going to represent the number of girls among 3 newborn babies. Okay, so X equals the number of girls born. So we have 3 newborn babies, and we've already done a sample space on this, at least I feel like we did, back in the previous chapter. So we went ahead and we looked at all the possibilities with 3 children. And so we came up with boy, 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 girl, girl, girl. And then we had boy, girl, girl. And then that boy, I wrote a diagonal so that I would consider all the outcomes where there was 1 boy. And that I was able to get that on the diagonal. That's how I came up with that. Okay, and then all the situations where there's just 1 girl. And again, I wrote that G in a diagonal so I didn't miss any of those. Okay, so this is something we had already talked about before. I talked about it back when we were using the probability of at least 1 equals 1 minus probability of none. And that example was under that formula from your chapter 4 notes. So anyway, I gave you the sample space. And this is the sample space when you have 3 newborn babies, or there's 3 children in a family. These are all the possibilities for boys and girls. And then we talked about why it's important to consider all the arrangements. For example, here the boy is the older child. Here it's the middle child is the boy, and then the younger child is the boy. So it's their birth order is different. Okay, so X represents the number of girls born. The number of girls born. So we could have 0 girls being born, we could have 1 girl being born, 2 girls being born, or 3 girls being born. So X is the number of girls born. All right, so you could see that the first scenario here, that's when 0 girls are born. So the probability that that happens, well, that's 1 out of 8, because there's 8 possibilities. Okay, let me change the color on the next one. All right, so for this one, it says X is 1. So how many cases do we have just 1 girl? Did I miss any? So I'm just looking for just 1 girl. That's just 3, right? Okay, so that's going to be 3 out of 8. All right, so the next one where X equals 2, now we're looking at the situation where we have 2 girls. So again, it's 3 out of 8, right? Trying to change the colors here so you see which ones I'm pointing to. And then the last case, when X equals 3, that's when we have 3 girls. So that only happens 1 out of 8. So X is our random variable. It's a discrete random variable because it's countable, 0, 1, 2, 3. It's countable. In this case, it represents the number of girls born. And then we have probabilities associated with each random variable. So the probability that 0 girls are born is 1 over 8. That 1 girl is born is 3/8, and so on. Okay, so in a probability distribution table, there's something hopefully that you noticed. The sum of your probabilities. If you have a probability distribution table, the sum of your probabilities will always equal 1. If it doesn't, then you're not looking at a probability distribution table. This probability distribution table is going to predict what will happen. Now the actual results can differ because of random chance, but this is a table that we use to predict what will happen. And I don't have to collect data. It's something that I already know. Because we have outcomes that are equally likely. When you're talking about whether a child is a boy or a girl, the outcomes are equally likely. All right, so you could add up the column for probabilities and see if it adds up to 1. And it does, right? Okay. So I'm going to come back to this example because there's other things that I want from this. I want to find measurements from this table. So I'm going to come back to this. For right now, that is what a probability distribution table looks like. The column, the probability distribution column has to add up to 1. Notice that there are no negative probabilities and there are no probabilities that are greater than 1. So we still use the same rules for probabilities. You have to make sure your probabilities are all between 0 and 1, including 0 and 1. Never bigger than 1 and never smaller than 0. Okay, so let me go ahead and take you to the next slide. So that's what I was talking about as far as the rules. So these are your requirements for a probability distribution, which I just talked about. Okay, so I want you to let's see, we'll do a poll on this. All right, so I'll call this A, this B, and this C. So right now what you're doing is you're voting on the table that represents a probability distribution. So based on what we just talked about, you should be able to know which one is a probability distribution. So just to remind you, if you haven't attended live, the voting is right next to the hand. Don't press the hand though, because that raises your hand. It's the letter A. You have to select. There's a drop-down menu. All right, so I'll wait until I see everybody selected something, and I know everybody's still there and listening. And there's still a few of you who are not typing in your last name. So remember, when you log in, you have to type in your last name. So Thomas, are you there? Ryoi? Okay, so there's still, okay, so go ahead and vote. There's still a few that are not there. So make sure you go to that icon at the top next to the hand and then select what you think is a probability distribution on here. So you're selecting A, B, or C. And make sure you take your mouse and hover it over the letter A so you can see the options. Do not press the hand. Okay, so let's see how you guys did. I have 23 in attendance today. All right, so Rebecca, you're there? Okay. And then Margaret. Laura, make sure you vote. Okay, I'll give you a few more seconds. Okay, so let's see how you did. This just allows me to take a break from talking, and it allows you to also make this more interactive. Okay, so it looks like the winner is B, and we still have some people not voting. Or you selected none. Oh no, you did vote, but you just selected none. Okay, so let's go ahead. It looks like okay, so it looks like B got the most votes. All right, so let's see why. Why was that the case? Okay, so nobody selected A, so I'll cross that out. And the reason A doesn't work is because you see that when you add up your probabilities, it does not equal 1. And that is one of the conditions. So remember, your probabilities have to equal 1, and that doesn't happen here. So that's not a probability distribution. And then, of course, you can cross out C, because look at that. We have a negative probability. So even though it adds up to 1, you have a negative probability. So that's not the probability distribution. So yes, the only one that works is B. So no negative probabilities, no probability greater than 1. And when you add up your column, it has to add up to 1. It has to add up to 1. And that happens for B. All right, so very important for you to remember the rules for a probability distribution. And that's what that exercise was. Okay, so we're going to be looking at measurements that can be obtained from this probability distribution table. So we have a formula for the mean, for the variance, and for the standard deviation. Now the standard deviation is just the square root of the variance. All right, so the ones that we're going to focus on are the mean and the standard deviation. Notice the notation for the mean. It uses Greek letters. So in this probability distribution, chapter, you are going to be using Greek letters for your measurements. Okay, so this is back to the example we had worked on. And I don't want to rewrite this all over again, but we're going to find the mean and the standard deviation. But I know I've already done this. I've already filled out the table. So I'm just going to go back to that table and find the mean and the standard deviation. Okay, so there's my table. And so I'm going to find the mean and the standard deviation. So let's go ahead and look at the formula. So to find the mean, it's the sum of x times p of x. That's how you find your mean. All right, so I'm just checking the formula, making sure I have that correctly. Yes, okay. And so you're first going to take, you're first going to multiply these out, and then you're going to add them up. Okay, so that's the formula for finding the mean. And so in this case, I'm going to take every value of x, and if it's helpful for you and you want to create a new column, then you can definitely do that. So that's what I'm going to do here, just to help you organize. So you can call this over here x times p of x. So this would be x times p of x. So you can just multiply across, because that's what the formula tells us to do, right? It just tells us we can multiply across. All right, so x times p of x, that's what this is doing. So x times p of x, 0 times 1/8 is 0. 1 times 3/8 is 3/8. 2 times 3/8. All right, so you have to remember your fractions, right? 2 times 3/8. So when you're multiplying your fractions, the 2 is the 2 over 1, so that gives us 6/8. So 2 times 3 over 8, that's 6/8. And then 3 times 1 over 8, well, that's 3/8. So what the formula tells us to do is to take our x and our p of x and just multiply them together, and that's all I've done. So I'm just going to clean up the rest here. Okay, so now I'm going to take my result from x times p of x. I'm going to take that result, and then I'm going to add it together. So that's 0 plus 3/8 plus 6/8 plus 3/8. So the mean, my denominator is 8, and then my numerator is 12. So the mean here is 12/8. Of course, we want to turn that into a decimal. But 12/8 is just 1.5. So that's what you would expect. If you had 3 children, you would expect that half of them would be girls and half of them would be boys. Now, I know it doesn't make any sense for you to have 1.5 girls or 1.5 boys, but remember, this is a theoretical model. So on average, we would expect that half of them would be boys and half of them would be girls. And 1.5 is half of 3 because we had 3 newborn babies. Okay, so let me go through this computation again. So first of all, what you have to focus on is the formula. So I just copied this formula from the notes from the previous slide. The formula says that you're going to take x, which is our random variable, times its probability. So x times p of x. So I have my column for x and I have my column for p of x. So that's the random variable and the probability. So the formula says multiply the two. And once you're done multiplying the two, then you're going to add everything up. All right, so I created a new column where I'm multiplying the two. So that's why it says x times p of x. So I took 0 times 1/8 0 times 1 over 8. That was 0. And then 1 times 3/8 was 3/8. And then 2 times 3/8 is 6/8. And then 3 times 1/8 is 3/8. And I took all these and added them together, and that's what's over here. Okay, and so I'm applying the formula. So that's a 1.5. So that's the mean for this. Okay, now I'm going to do the same thing, but now I'm going to find the standard deviation. So I'm going to take the same table, and now I'm going to find the standard deviation. Okay, so the formula for standard deviation is different. Okay, so let me go ahead and copy the table over here. So this is the same table I was working with. X, P of X. So we had 0, 1, 2, and 3. And then we had 1/8, 3/8, 3/8 again, and then 1/8. And then what I had over here was X times P of X. Okay, now the standard deviation formula is different, so I may not need X times P of X. So let me write it first and see if I need it. Okay, so the standard deviation, which the notation for a standard deviation using the Greek letter, it's sigma, but it kind of looks like a 6 turned a bit on its side. So that's your sigma. So sigma equals the square root, and it's the sum of x squared times its probability. So the sum of x squared times the probability, and then you do that first. You take x squared times p of x, and then you add up all your results and subtract from the mean. And the mean has to be squared. So that's me just copying the formula from your notes. So it looks like we don't need x times p of x, we need x squared. Okay, so what I'm going to do is I'm going to create a different column for x squared, just so that we keep everything organized. So that's what I'm doing here, is now I'm going to take x and I'm going to square it. So I know where my column of x is, I just need to square it. So 0 squared is 0. 1 squared is 1. So I'm taking each random variable and squaring it. So 2 squared is 4, 3 squared is 9. So I took everything in that column and squared it, and now I have its own column that's labeled as x squared. So now what I need to do according to my formula is I need to multiply x squared and p of x. I need to multiply x squared and p of x. So I need to multiply these two. Okay, so that is a new column. And again, this just helps me organize all my information if I leave it in a column. So x squared times p of x. Okay, so that's what I'm doing. I'm just multiplying those two columns. So I'm going to get 1/8. So let me change the color here so you see what I'm doing. So I'm going to take 1/8 times 0. Now multiplying that out, well, that's just 0. Multiplying 3/8 times 1, and that's 3/8. Now multiplying 3/8 times 4, and remember we multiplying fractions, so 3/8 times 4. 4 is just 4 over 1. So multiply the numerator, multiply the denominator. So we're multiplying fractions. You make sure you multiply the numerator and the denominator. So this is 12/8. And then finally over here, we multiply x squared and p of x, and that's 9/8. Okay, now look at the formula. I'm supposed to take my result from x squared times p of x. So I'm supposed to take my green numbers here, which is what I ended up with when I multiplied x squared and p of x. And I'm supposed to add it. Add those numbers together. That's what this symbol says. I need to add that. All right, so I'm just following the formula. Okay, let me clean this up so I can continue. Okay, so here I go. Standard deviation is equal to the square root. So if I add all that up, what do I get? So let's add that up. So I have 0 plus 3 plus 12 plus 9. So type out what that is. I just want to make sure you're following along. So if I add up that column, what do you get? Okay, so do you all see the yellow part? All right, so when you added that up, you are all getting 3, right? Okay, you've already reduced it. Okay. All right, so I know what that is. I know that that part, I keep drawing the square root and it keeps going in a very odd way. Okay, so let me try that again. Square root. So we have the 24 over 8, right, which is where you're getting 3 from, right? So that part of the equation is just 3 minus the mean squared. Now, we already had the mean. That was the previous calculation we did. The mean was 1.5. The mean was 1.5. All right, so that's what I'm going to use. 1.5, and I square that. Now, the mean, you have to make sure it's not rounded. This one was a terminating decimal, the 1.5, but sometimes you're going to have to round it. And so you want to make sure that when you're using the mean to calculate the standard deviation, make sure you're using the unrounded mean. Okay, so that's what we end up with, and some of you already have the answer to that. So don't forget to take the square root of that. So 3 minus 1.5 squared, and then make sure you take the square root. All right, so I'm getting a couple different answers. So let me show you how I entered that on the calculator. So unless you did it, yeah, so let me just show you how I entered it. All right, so on the calculator, I'm going to clear this. Let's clear. So it was the square root. So there's the square root key of, it was 3 minus 1.5 squared. So the square key is right diagonal to the 7. And then I have to get out of the square root and then press enter. So notice that I was able to do that all inside the square root. Okay, so it looks like now we agree on that. Now, how we round this, if you look at your random variable, they're whole numbers. And so we're going to round to one more place. So we're going to round to the 10th place. Okay, so that's that's how I do this. Of course, you're going to, when you do the homework, you have to, read the fine print because sometimes they change their mind about that. So you want to make sure you're always reading what the rounding instructions are. Okay, so you've all typed out what I have there, 0.866, good. Okay, so 0.866025, and then it continues. So I'm going to say that that's 0.9. So the random variable, the discrete random variable, is their whole numbers. So I'm going to round this to one more place than what we see here. So I'm going to round it to the 10th place. Okay, the mean was rounded to the 10th place as well. That was from the previous calculation. So using a probability distribution table, you should be able to get the different measurements. The standard deviation is 0.9 and the mean is 1.5. Now, this is the only time I'll do this calculation by hand. You are able to use a calculator as well to do this, but it's good for you to know how the formulas work. You need to know what the symbols are, and you need to know how to do basic arithmetic to follow the formula. One of the questions I asked you on the midterm is I actually asked you to show me how the formula works. So you actually have to use the formula. All right, so on the calculator, this is how we would go about it. So on the calculator, the random variable, that is your L1. Your probability is your L2. So if you're doing this on the calculator, it's just going to be a 1 var stats on L1, comma L2. And you've done this before in chapters 2 and 3. So your random variable goes in for one list and your probability goes into a different list, and you just do a 1 var stats. It's going to give you your mean and it's going to give you your standard deviation. All right, so I'm going to show you on the calculator how we get that. All right, so I just cleared my history. So I'm going to go to Stat. Then on Edit, I have information in there, so I'm going to clear that. I go up to the name of the list, press Clear, and then come back down. So remember, our random variable, that was one of the lists. So I'm entering the random variable. We have 0, 1, 2, and 3. Then I'm going to go over to the next list, and that's my probability. When I enter it as a fraction, the calculator automatically turns it into a decimal. And that's okay. Just know that it's doing that. So 1/8, 3/8, and then 3/8 again, and then 1/8 again. So one list are that's your random variable, and the second list, those are your probabilities. So I'm going to do a 1 var stats. So I'm just curious, does anybody know how to get to 1 var stats? What key do I press to get to 1 var stats? This was back from chapters 2 and 3. Okay, so I see the stat key got a lot more votes on that. It's just kind of looking at the answers as they were scrolling up. All right, so let's try the stat key, see what's underneath there. So stat is where you go first, and then we're going to get to calc, right? So stat, and then when you press the stat key, the window, that menu has calc at the very top. So that window gives you a menu which has calc at the very top, and that's what I'm selecting. Okay, so there's the 1 var stats. So I went to Stat and then right arrow to Calc. Okay, so press Enter. and this is the screen I get. Now, if you have the older version of the TI-84, then what you see on your screen is 1-bar stats, and you have to type in L1, L2, just like I wrote it on the whiteboard. You'll have to type in L1, L2. So you'll have to do second, the number 1, comma, second, the number 2. But on this one, I can just go down. Okay, so my list is L1, that's my random variable, and then my frequency list, that's going to be L2. Those are my probabilities. So this time, your frequency list is a probability, and your list is your random variable. You have to make sure it's in that order. So L1 goes first, and then L2. So your random variable, and then your probability. So I'm going to go ahead and select Calculate. Okay, now I'm looking at that screen and it doesn't look anything like what I had in my formulas. So I'm going to go ahead and take a snapshot of that and move it over to the whiteboard. Everything I need is there, but the calculator gives me my information very differently. I mean, it's not what I would expect. So look at this. There is the mean, but look at the notation it used. So the calculator will give you X bar, but when you write this out on paper, you need to make sure that you correct it. Because in chapter 5, we're using Greek letters to talk about the measurements. So the properties of a probability distribution require us to use mu and sigma. All right, so look at what happened here. Do you see this part here? What happened to the standard deviation? It's blank. So S is left blank. So what do I use? Right, so there's a reason why that standard deviation is left blank, because remember the notation we're using isn't S, it's sigma. So hopefully that's a clue letting you know that you're not going to write S, but instead you have to write sigma. And so that's exactly what we ended up with, right? 0.9 if we round it. So be aware that the window you get after you do the 1-bar stats, you have to make some adjustments. So instead of writing X bar, you have to write mu. And instead of writing S, you have to write sigma. And so it's nice that it leaves S blank, so then you know you're supposed to choose sigma. So you will be marked off if you use X bar and S on the exam. So you want to make sure you're using the right notation. So then that's an example of how you could do this using your calculator. So I showed you how the formulas work. We found our different measurements using the formulas. And then I also showed you how you would do this on the calculator. So that is the end of example 3 where I asked for the mean and the standard deviation. Okay, so now I'm going to move on to the roundup rule, which I was actually using without showing you the definition here. But I was using the roundup rule that I have here. And what this says is that you're going to round your results by carrying 1 more decimal place, and then the number of decimal places used for your random variable X. And that's what we did. Okay, so now we're going to talk about identifying unusual results. So this is something we've already discussed. We talked about the maximum usual value and the minimum usual value, but now the notation looks different. So remember, in chapters 2 and 3, we had the mean plus 2 standard deviations and the mean minus 2 standard deviations. We still have that, but the symbols that we're using are not the same. So just keep that in mind. Now we're always using the Greek symbols for this chapter. Okay, so I'm going to move on to something called expected value. Now look at the formula for expected value. Does that look familiar? The expected value of a discrete random variable is denoted by using that capital letter E, and it represents the average value of the outcomes. So it gives you the average value of the outcomes, and it is obtained by finding the value of, well, you have to find the sum of x times p of x. So that formula looks really familiar. We've already used it before, but we didn't call it E. What did we call it? Right, that was the formula for the mean, right? All right, so this is one of the questions on the lecture assignment that you have to do to get credit for watching this lecture, is that the expected value and the mean is the same thing. They're the same formula. The expected value of a probability distribution is the same as the mean of a probability distribution. It represents the average value of outcomes. It's the same formula. So I've already showed you how to find the mean using a probability distribution. I used the formula, and I also used the calculator. So that's how you're going to find the expected value. Now, this is an example, or this is a situation where you would use an expected value. So we have several questions having to do with gambling or insurance. And so we always interested in finding out what the expected value is. And so this one has to do with, again, another lottery situation. And this one says, at various times, the state has a pick 4 lottery in which you pay $1.50 to select a sequence of 4 digits. Now the digits we're selecting go from 0 to 9. So how many total is that? Good. Okay, yeah, don't forget to count the 0. So that's a total of 10. All right, don't forget to count the 0. So if you're counting from 0 to 9, that's 10. All right, so we have a sequence of 4 digits. So we have 1, 2, 3, 4. Those are our 4 digits. And we can select the numbers from 0 to 9. The digits selected may repeat. So if I wanted to select the number 0 4 times, I could do that. The digits may repeat. If you win by selecting the same sequence of 4 digits that are drawn, you collect 11,700. All right, so I'm trying to find out how many possible combinations there are, or how many possible outcomes there are. So the first, I have 10 numbers to choose from. Now it says the digits may repeat, so then for the next one, I have another 10 to choose from. Again, the digits may repeat, so for the next, I again have 10 to choose from, and so on. All right, so this state has a Pick 4 lottery. So I'm selecting a sequence of 4 digits, and I'm using the numbers 0 to 9. So I have 10 numbers I can choose from. So that means every time I can choose 10 because you're allowed to repeat. So that's the number of selections possible. That's this part right here. So that's 10 to the power of 4. So that's how many ways this can happen. All right, now it says find the expected value for this Pick 4 lottery. So to find an expected value, I need a random variable and I need a probability. So I need an x and I need a p of x. To find an expected value, I need a column for my random variable and a column for my probability. So the random variable takes into account the possibilities here. You either win or you lose. That's only two outcomes here, so either win or you lose. Okay, so in the case that you lose, it cost you $1.50 to play this game. That's how much was paid. So if you lose, you're out $1.50, and we represent that by making it negative. So this is the case that you lose. I'm going to label this L, and then we'll label this one as W. So you lose or you win. Okay, now what is the probability of losing? Well, there's 10,000 possibilities. That's your denominator. And so your numerator, out of those 10,000 possibilities, out of those 10,000 outcomes, how many of them are not going to be the winning outcome? Well, let me ask it in a different way. How many of these will be the winning outcome? 1, yeah. Okay, so only 1 out of the 10,000 will be the winning outcome, right? And then how many we have left is the rest. 9,999 is how many we have left. So only 1 is going to be the winning outcome, right? Only 1 selection of 4-digit numbers is going to win. So the probability of losing is very high. If you take 9,999 and divide that by 10,000, you're going to get a number that's really, really, really close to 1. Okay, so you have to consider what happens when you lose, and then we're going to consider what happens when you win. So when you win, you have to make sure you subtract how much you paid to play the game. So it's always going to be the winning minus how much you paid to play the game. So the winning is 11,700, but you need to make sure you subtract how much was paid to play the game. So when we subtract that, we get $11,698.50. All right, so we have the scenario, you lose, you win, and so you have to account for both of them. Okay, so we're going to find out what the expected value is. Now, if the expected value is equal to 0, that means we break even. So neither the player nor the state is making any money here. So expected value equal to 0, that means we break even. Now, if the expected value is greater than 0, that means the player is favored. Or let me write, well, that's supposed to read that the player is favored. So it favors the player. Let me see if I could change that. Favors the player. And then if the expected value is negative, then it favors the casino, or it favors the state, or whoever is sponsoring this game. So in this case, it favors the state, or favors the house. All right, so we have to pay attention to what the expected value is going to be. Now, if the state has this pick 4 lottery because it's trying to increase its revenue, then we would expect that the expected value would be negative. And if the expected value is not negative, then the state has to charge more than $1.50 to play this game. So if the state is using this to increase its revenues, then we would expect that our value for E would be negative. So let's see if that's the case. All right, so the formula says that we're going to take, and let's see if I change my colors here so you can follow along. So I'm going to multiply X with its probability. So I'm going to multiply these two. So that's negative $1.50 times the probability. So we have a numerator, we have a denominator. That's our probability. So again, we multiply X with its probability. So that's the winning minus what was paid to play the game. So that gets multiplied by 1 over 10,000, which is the probability of winning. Okay, so that's what the formula tells us to do. For expected value, you take X and multiply it by its probability. And then you add your results. Now, if you put that in your calculator, round that to the nearest cent and tell me what you get. So you're entering that in your calculator and rounding it to the nearest cent. So far I have an answer. Okay, so I have $1.02. All right, so I'll give you another minute for those of you who are still figuring it out. I'm going to bring up the calculator and then we could see if we can come up with it together. All right, so it looks like we have a popular response there, a negative 0.33. All right, so it looks like it's favoring the state then. So our expected value is negative 33 cents. So this means that the state is making 33 cents on every purchase of a lottery ticket. So we would expect that on average, the state is making 33 cents because it's negative. It favors the state. Okay, those of you who didn't get 33 cents, follow along with what I'm going to do on the calculator. So 33 cents is the correct answer. You want to round it to the nearest cent because we are talking about money. Okay, so I'm going to go ahead and clear here. Clear. And so I forgot, yeah, I entered it, I think it was a negative 150. And that was multiplied by the probability. I'm going to go ahead and put parentheses around the probability. It was numerator and then denominator. And I think there were 4 zeros. And then I added that to 11,698 with 50 cents. And that was multiplied by the probability. So just make sure you've typed in your numbers correctly, and that's what we had. And so if you press enter, that should give you your expected value. Notice that my probabilities were in parentheses. All right, so it is 33 cents, negative 0.33. And so since our expected value is negative, it favors the state. And someone said you did the same thing, but you got negative 3.3. I would again check your calculator one more time if you're probably missing a digit. So yeah, just go back and check your numbers that you've entered. So it was negative 150 times, make sure your probability is listed just as we wrote it down. So I would check the numbers, make sure you have all those correctly. All right, you were missing a 0. And so you see how very easy it is to make a mistake. So always, always go back and check. Check, make sure you've entered things correctly. All right. So I'm going to give you one more example. I'm just trying to think of how the questions I asked you on the lecture, after the lecture today, so I want to make sure I covered everything. As we have about, what, 20? We're done at 2:20. Okay, so we're almost there. Okay, yeah, so I'm going to go ahead and do one more problem. And here's this one. Again, it's an expected value problem. It's talking about an insurance company. So we have a 28-year-old man who pays $240 for a one-year life insurance policy. Now the coverage on that policy is $90,000. We know that the probability that he will live through a year, we know that to be 0.9994. So somehow the insurance company has already done its research and found out that that's the probability that this 28-year-old man will live. So what is the expected value? So I know I'm supposed to use expected value because it asks for the expected value here. So underlining it. We want to know what the expected value is for the insurance policy. If the insurance company is not interested in making a profit, what will it charge this 28-year-old man? All right, so I need to find an expected value, so I have to start off by making a table, a probability distribution table. That probability distribution table, we have to have a random variable x and a probability associated with that random variable. All right, so the man either lives or dies. So lives or dies. Now, if he lives, the probability that he lives is given to us. That's 0.9994. That's the one that's already given to us. So remember the property for a probability distribution table. If we add up the probabilities in our probability distribution table, what was that supposed to equal? Okay, so it's supposed to equal 1. And so then if it's supposed to equal 1, then we should know what the probability of dying is. If we know the probability that he lives, we should know the probability that he dies, because whatever adds up to 1, right? Okay, so we just have to subtract it from 1 and we get the probability that he dies. Okay, now if he lives, he's already paid $240. So that's it. He's paid $240. So that's a negative amount because it's out of pocket. So it's just like that lottery game. You pay to play. So if you do not win, you're in a negative. You're at a negative or at a loss. So that's what happens here. If he lives, he's paid out $240. So the random variable x would be negative 240. Now, what happens here is if he dies, there's 90,000 coverage. Now, he doesn't get the $90,000, right, because he's dead, but his family or his estate gets the $90,000. All right, so what we would put here is the 90,000 minus the 240, minus what was already paid out. So that's how we come up with this 89,760. So remember, we have to make sure we subtract how much is paid to the winning, or in this case, to the coverage, what the family is getting. So you're going to do 90,000 minus 240. And that's what gives you the 89,760. So you have to create a column for your random variable and a column for your probability to find an expected value. Once you do that, then you can just use the formula. Now, if you prefer to use your calculator, then this would be L1 and this would be L2. So if you rather use the calculator, you can. And you can do a one-bar stats. I don't know on this one what would be easier, because we don't have that many random variables, so it might be easier just to use the formula so you don't have to go over to the calculator. But either way, I'll use the calculator this time since I used the formula last time. So remember, you have a column for the random variable and a column for the probability. So if you use your calculator, you need to enter each column into your calculator. All right, so I'm going to move on over to the calculator. And so I have to go to Stat. That's where I start. Then over to Edit, because I still have to enter. All right, so I have information in my L2 and my L1, and I'm going to clear that. So for L1, I have negative 240. Now be very careful, those of you who are typing in negative 240. Do not type in the minus. You have to make sure you're typing in the negative. The negative is at the very bottom. The calculator does not like it when you put a minus instead of a negative. So I'm pointing here to the negative. That's what I used. And then 89,760 is my next entry. Okay, now for the probability that he lives, that was 0.9994. So it's highly likely that he will live. And then it's unlikely that he will die, 0.0006. Notice the calculator turns it into scientific notation, or its version of scientific notation. And that's okay. Let's just leave it that way. Okay, so once your random variable is an X and your probability, or once your random variable is an L1 and your probability is an L2, now you can do one more stats. Okay, so random variable, which is our X, that's an L1, and then probability is an L2. You're going to go to stat and then over to calc, and then it is going to be the one of our stats. I press enter. So remember, L1 is your random variable that goes into your list. L2 is your probability that goes into your frequency list. And then you press calculate, or over the word calculate, and press enter. All right, so I don't see a symbol there for E. So what should I do? I do not see a symbol for E. And I was trying to get expected value. So what is it? What on the calculator, what do I know about how this calculator gives me my information? I should know E from here. Right, you guys remember that the expected value and the mean have the same formula. The expected value and the mean have the same formula. So on this calculator, although it doesn't say mu, this is the mean. It's negative 186. Again, the calculator gives you X bar, but you're not writing that down. Remember that we either have mu or the expected value. So it looks like $186. Now it's negative. So does this favor the player or the casino? So in this case, does it favor the 28-year-old man or the insurance company? We ended up with a negative expected value. It was negative 186. So does it favor the 28-year-old man or the insurance company? Right, the insurance company, right? They're making money off of this policy. So on average, the insurance company is making $186 on this policy. Right? Okay. So the first part of this is asking you for the expected value, and that's what we have here. So the expected value is negative 186. It favors the insurance company. It favors the insurance company. Okay, so there's a second part of the question here. The next part is asking you if the insurance company is only interested in breaking even, what should it charge the 28-year-old man? So if the company is not interested in making a profit, what should it be charging? Well, right now, it's charging too much because they're making $186. So you see the $240 that they're charging? On $240, they're making $186. So they're charging too much if their goal is to break even. So they should probably charge less at $240. Now here's a quick way of figuring out how much less they should charge. So to break even, how much should they charge? You're going to take the amount paid and you're going to add the expected value to that. And your result is going to be the new amount that should be charged in order for them to just break even. So the amount paid, that was $240. The expected value happened to be negative. So if you take 240 plus a negative 186, that's the same thing as taking 240 minus 186. So the result, which I see you typed out, $54, that's how much the insurance company should pay if they're only interested in breaking even. That's how much they should charge for this insurance company. Or that's how much they should charge for this insurance policy. That's how much they should charge for this insurance policy. So one of my favorite questions when it comes to expected value is fundraisers. If you're thinking of having a fundraiser and you're selling tickets, and of course only one ticket or maybe a few tickets are going to be the winners, you can set the price of that ticket to make a certain profit. And we'll talk about that later. It's one of my favorite questions to ask. So an application to this in maybe your real life is to, if you're doing a fundraiser, how much do you have to charge per ticket if you're interested in making so much profit? You could set that using this expected value situation. Okay, so the last thing I want to get to, because I did ask it on the lecture questions that you have available, I just am going to go over one more thing just because I remember that I did ask you that question. Let's see, before I go there, I have a question here that says, doesn't it all depend on how many tickets you sell? So, right, because you have to know how many tickets are out there. So I'll go ahead and give you that type of example. But yes, it's the number of tickets you sell will turn out, it'll give you the probability of winning. So the more tickets you sell, the smaller the probability of winning is, right? Because say you have 100 tickets and you sell 100 tickets and there's only one winning ticket, well then in that case, your probability for winning is smaller than if you only had 10 tickets that you sold. Then the probability for winning if you only sold 10 tickets would be higher. So that would affect your probability. But yeah, we'll definitely talk about that. I'll go ahead and give you that example. I don't have it in the slides right now, but we'll go ahead and look at it. Okay, so that is the end of it. That's the end of our section or of our lecture today. But I wanted to give you a preview of what's to come. We have special types. Here it is. That's the slide I wanted to get to. We have special types of probability distributions. One is called the binomial probability distribution. That's this one right here. It's called our binomial probability distribution. And there's 3 ways to solving binomial type problems. We could either use a calculator, we have tables, and we have a formula. And so the most efficient way for solving binomial type problems is by using our calculator. So I had to get to that slide because that's the last question I asked you on your lecture questions today. And so that is the answer to it. So we're going to actually talk more about this because I didn't get this far. But the question where it asks you what is the most efficient strategy for solving binomial probabilities, the most efficient strategy is to use your calculator. And we will continue our discussion with binomial probabilities next time, and I'll find another example for you on the expected value as well. Okay? All right, so we'll talk to you next time.